In this demonstration, we're going to have a look at the conservation of momentum and the conservation of kinetic energy involved in one-dimensional collisions. What I've got here are two trolleys, and these enable elastic and inelastic collisions to take place. The ones which allow elastic collisions to take place have a notice on here which says caution magnetic. So what happens when we have them together is that the magnetism pushes them apart, and that means that there's no contact between the two. The second thing, before we actually do this experiment, that we need to check is to find out whether or not this is perfectly level, because if it isn't, what it means is that the force of gravity has an effect on the whole system, the two trolleys and the masses. So if we just sit it on there and let it go and see if it moves, and it's not moving, so that means to say that we've got this level. So we're going to do a variety of collisions. We've got 8 collisions altogether. Firstly, stationary and equal masses, and they'll be elastic. Then it'll be inelastic, and down here we've got them both moving, elastic, and then here we've got them both moving and inelastic. Similarly here for different masses. Here they're stationary, here are stationary but joining, and here elastic and inelastic. And these are all covered by this list of aims. You can see there the 1, 2, 3, 4, 5, 6, 7, 8. And the first is, as you can see from the book, an elastic collision. So they aren't going to come in contact. We're going to have one mass here that is still, and one mass here which is allowed to collide in with this. Before we do that, we need to set up the computer, so I'll show you how to do that. So this is the setup here. So what we've got to do is just check that our sensors are in place. So we've got those 2 sensors, and that's okay. So we close that. Next, double click on the top right there and do this twice to get 2 graphs. So one of these graphs we're going to use to monitor the movement on the right. So I'm going to click just the velocity. This is all that we're interested in, and you might be able to see that's velocity channel P1, and over here click this velocity channel P2. Now I've got to make sure which sensor is which, so I'm just going to do a test. I'll start the recording here and push one of the trolleys. So that indicates to me that the trolley that is on my right as I'm doing the recording is this one here, which is actually on the left on the screen. So I'm going to label this as the right trolley. Now we're in a position to start recording. What we'll be able to do with our computer there will be to have a look at the velocities of each of these before and after the collisions. We'll know their masses. Each trolley here is half a kilo. This additional mass is half a kilo. We can record those masses in the table and then calculate both the momentum before, the momentum afterwards, and see if momentum is conserved. We can calculate the kinetic energy before and the kinetic energy afterwards and see what's happened to the kinetic energy. So let's record our data. Now here you can see the place to record the data. Here is the first mass, mass A or trolley A. So that is all 0.5 of a kilogram. The second mass is 0.5 for the first one because they're the same. And then the second is a different mass, namely 1 kilogram. So the first one I'm going to do is one in which I have this one stationary, and I'm going to collide this one into this one elastically, and the two have equal masses. This is the kind of graph that we get as a result of our recordings. Notice here that the positive direction of the motion is to the right, and the initial velocity of the trolley was 0.46. When it collided, it became 0. Over here, the initial velocity was 0, and it became a negative velocity because the sensor is at the far end, and what it means is that the trolley is traveling towards the sensor. So anything on this side, the right side of this screen here, where it's negative, we have to change it to positive, and positive to negative. So you can record now those values into the table as indicated here on the screen. Our next collision is between two equal masses. This time they are undergoing an inelastic collision. So these are the results of the second collision, and as you can see there, the initial velocity was 0.61 meters a second, and the final velocity was 0.3. Whereas over here on the right, the initial velocity wasn't 0, it was 0.01, so some slight movement there, and then the second one is plus 0.30 meters per second. We've got to change that to positive. So again, we can record that now in the table for the data. Now we've got two that are going to be moving. Again, this one here is going to be an elastic collision. We've got the magnet there. So for the third collision, we've got 0.03 here, 0.3 for the final. Over here, we've got minus 0.33 and plus 0.27. So those bits of data go there in the table. Now we've got two equal masses, and they'll be colliding inelastically. In other words, they'll be joining. So here the figures are 0.35 and 0.01. Up here minus 0.32, and down here plus 0.01. Notice the way in which in inelastic collisions these two are the same. Now we've got an example of two different masses. This one here has got an additional 500 grams or half a kilogram added, so that's a total of 1 kilogram, and this one here is half a kilogram. So we'll have this one here stationary, and we'll have this one here moving. So here we have figures of 0.61 and minus 0.15 and 0 and plus 0.37. So that's where they can go now into the data table. Right, this time we've got two masses in which this one here is different to that. In other words, this one here has got 1 kilogram, and this one here is half a kilogram. This time this one will be, we'll just have the one moving. So initial velocity there is 0.62, final velocity 0.20. Over here we've got a of 0 and plus 0.20. So again, that figure there is to be positive 0.20. This time we've got two unequal masses, and both of them this time will be moving, and the collision will be elastic. So figures of 0.43 minus 0.38, 0 minus 0.25 and plus 0.14. And after that we'll have an inelastic collision with two moving. So figure thereof 0.5 minus 0.09, over here minus 0.32 and minus 0.09. Again, note how those figures for the final velocity are the same in the situations where the two trolleys stay together. We're now in a position to put all of this data into a spreadsheet. And as you can see here, we've got the masses, the two masses. Here we've got the second mass with a mass of 1 kilogram. Otherwise, the masses are 0.5. Here are the initial velocities, u1 and u2. And here are the final velocities, v1 and v2. That enables us to work out the momentum before. Now, to do that, we can put in here a formula. And as you can see from the formula up here, what it does is it multiplies the mass times the initial velocity here and the mass and the initial velocity here and adds those together. And over here with the final momentum, it's a similar story. If we click on that, you can see the relevant cells here. We're going to multiply the mass times the initial final velocity and the mass times the final velocity. So once we've got those formula in these cells, what we all just need to do is fill down, and that puts that formula into each of these cells and gives us the initial momentum. And pulling this one down, we get the final momentum. Now, as far as the kinetic energy is concerned, we can use a similar sort of formula. And here what I've got is half the mass times the velocity squared plus half the mass times the initial velocity squared. We've added those together. And similarly over here, we've got half the mass of the first times the velocity, that's the second, that's the final velocity there, and again half the mass times the final velocity. Again, we can pull that down, fill down, putting that formula into each of these. Now this gives us the enough information now to create the discussion or the conclusions. So first of all, we look at whether or not momentum was conserved. So if we look at these two here, they're exactly the same. So we can type in here, yes. Over here, there's a very, very small difference. So I'm going to type in yes here. Here, they're exactly the same. So yes. Here, there is a bigger difference. So perhaps we're not quite justified in saying yes. Here, the difference is very small. So I'm going to say yes. And here again, the percentage difference, we might argue no case, but it's on the edge, isn't it? So down here, we can say yes. And here, there is a difference, and perhaps we could argue no there. Now, as far as the kinetic energy is concerned, what we're interested in is the change in kinetic energy in these collisions. So what we've got to do is put in here a formula. And in fact, so what this is the difference between the final kinetic energy and the initial kinetic energy divided by the initial kinetic energy and then multiplied by 100. So that formula is in there, and in this particular case, the answer is no. We'll fill this down to see what happens with the rest. So there's certainly been a loss of kinetic energy in this second one here, which, as you can see, is a inelastic collision. That's what the code over here means. As far as the next one is concerned, there's 18% loss in this elastic collision. Here we've got 100% of the kinetic energy lost. Here with this elastic collision, it's down to 20. And here with this inelastic collision, we've got 69%, as we can see, and this other one here, 93%. So certainly with our elastic collisions, we've got what we might call a not perfectly elastic collisions. It's very, very difficult to get what's called a perfectly elastic collision. And here is actually one. Apart from that, what we do notice is how the elastic collisions here of 18, 20, and 48, those collisions, certainly there is less kinetic energy lost in comparison with the elastic collision. So here there's just over half, here it's 100%, here almost 70, here close to all kinetic energy lost. So that's the point that we can come to when it comes to our conclusion that with elastic collisions, there is little or no loss of kinetic energy, and with inelastic collisions, there is much more kinetic energy lost.